The black between the stars is not empty. It is filled with a strange cosmic soup, the interstellar medium. This vast expanse of gas, dust, and radiation holds secrets that rewrite our understanding of the galaxy. By the end of this journey, you will know 30 of its deepest mysteries, from missing atoms to the possible seeds of life itself. How could a cloud in space be colder than the afterglow of the Big Bang? What are the giant bubbles blowing from the heart of our Milky Way? We are about to dive into the enigmas hidden in plain sight in the so-called voids of space. Which cosmic mystery do you find most compelling? Our first mystery is one of cosmic bookkeeping, a discrepancy so vast it involves half the normal matter in the entire universe. According to our best models of the Big Bang, a specific amount of ordinary or baryonic matter was forged, the protons and neutrons that make up stars, planets, and us. Yet when astronomers add up everything they can see, from glittering galaxies to the faintest gas clouds, they only account for roughly 50%. Billions upon billions of solar masses of atoms are simply missing. This is the missing-baryon problem, and the prime suspect for their hiding place is the interstellar medium, or rather, its even more tenuous cousin stretching between galaxies. Theorists propose that these lost atoms are not in clumps but spread in a ghostly, superheated plasma called the warm-hot intergalactic medium, or WIM. This material is so diffuse and so scorching hot millions of degrees that it doesn't glow in visible light. It whispers instead in far more energetic tones, the faint ultraviolet and X-ray signatures of oxygen and other heavy elements being stripped of their electrons. Finding these whispers is a monumental task. It requires space telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory to stare at the faint filaments of the cosmic web, the vast scaffolding of the universe, hoping to catch a spectral flicker from this elusive material. The hunt is like trying to see the heat haze above a distant road on a blistering day, but the road is a filament of gas 10 million light-years long. If we can finally map the WIM, we will not only solve a fundamental accounting error, but also trace the complete circulatory system of the cosmos, revealing where all the ordinary matter truly resides. But if atoms are missing, what incredible things might be hiding in plain sight? Deep within the cold, dark nurseries where stars are born, astronomers have stumbled upon a treasure trove that defies expectation. Floating in the frigid voids of molecular clouds where temperatures hover just a few degrees above absolute zero are the building blocks of life itself. We have found sugars like glycoldehyde, the simple alcohol of ethanol, and even amino acids, the very components of proteins. This is the second great mystery. How do these complex, fragile organic molecules form in an environment seemingly designed to destroy them? Space is bathed in brutal radiation and is profoundly empty. The chance for two atoms to meet and bond into something more elaborate seems astronomically low. The answer lies on the surfaces of microscopic dust grains. These tiny particles, smaller than a wavelength of light, act as cosmic laboratories. In the deep cold, atoms and simple molecules like carbon monoxide stick to their surfaces, losing energy and becoming trapped. There they can slide and meet other tenants. A grain of dust becomes a sheltered workshop where, over millions of years, through a slow chemistry we are only beginning to understand, simple ingredients are assembled into the complex compounds of life. Radiation, rather than only breaking things apart, might provide the energy for some of these bonds to form. The implication is staggering. It means the fundamental ingredients for biology are not unique to Earth, but are being manufactured on an industrial scale across the galaxy, in the cold clouds between the stars. These prebiotic molecules, frozen onto dust, eventually get incorporated into new solar systems. They could have rained down on a young Earth, seeding our oceans with the organic compounds that would one day spark into living cells. The interstellar medium, therefore, is not just a void. It is a vast, dark chemical factory, quietly assembling the pieces of the puzzle long before a planet like ours even exists. What other recipes is this cosmic kitchen quietly preparing? These dark chemical factories have a visible form, and they are some of the most hauntingly beautiful structures in the cosmos. Drifting against the backdrop of the Milky Way starfields are vast, shapeless voids of blackness, regions where the light of distant suns is completely extinguished. These are the dark nebulae, our third mystery. They are not empty holes in space. They are immense, cold clouds of gas and dust so thick they act like a cosmic velvet curtain. The iconic Horsehead Nebula in Orion is a famous example, a dark silhouette of dust sculpted by stellar winds into a familiar shape, but their beauty masks a profound question. Inside these opaque clouds, the density is perfect for new stars to be born. Gravity should be pulling the material together, yet these clouds can remain stable for millions of years. What, then, is the final trigger that causes one to suddenly collapse and ignite a stellar nursery? The answer lies in a fragile balance of opposing forces. Gravity constantly pulls inward, trying to compress the cloud. Pushing back is the cloud's own internal gas pressure, and more importantly, a network of incredibly powerful magnetic fields that thread through the dust like invisible wires, providing a supporting structure. The third player is turbulence, chaotic, supersonic motions within the cloud, like a storm on a galactic scale. For a star to form, something must disturb this equilibrium. It could be the shock wave from a nearby supernova explosion slamming into the cloud. It could be the collision of two clouds or the focused pressure of radiation from massive stars on the cloud's surface. This disturbance creates a dense knot where gravity finally wins, and a protostar begins to form, hidden from our view. For centuries, these dark nebulae were impenetrable. Now, telescopes that see in infrared and radio light, like the James Webb Space Telescope and the Atacama Large Millimeter Array, are our tools for peering inside. They can see the heat glow from the dust itself and detect the faint radio signatures of molecules, allowing us to map the intricate structures and magnetic fields within. We are watching the very first moments of stellar birth, unraveling the recipe that takes a cloud of frigid dust and sparks it into a sun. Yet these dark nurseries are not the end of the story for the material between stars. It has an escape route, one that leads to a structure so immense it redefines our view of the galaxy's very architecture. In the 1980s, astronomers mapping the sky in X-rays made a startling discovery. They found colossal tunnels of superheated gas, each one stretching for thousands of light years, rising perpendicularly from the Milky Way's star-filled disk like the pillars of a cosmic cathedral. These are the galactic chimneys, and they are our fourth mystery. Picture our galaxy not as a flat, static disk, but as a dynamic engine with a built-in ventilation system. These chimneys are the exhaust pipes, and their power source is the most violent events in the stellar life cycle, supernova explosions. When a massive star dies, it does not go quietly. It unleashes a blast wave of unimaginable energy, shredding the surrounding interstellar medium and carving out a bubble of million-degree gas. Now, imagine not one, but hundreds of these explosions occurring in a chain reaction within a star-forming region. Their combined fury can punch a hole straight through the thinner gas of the galactic disk, creating a conduit that channels this scorching plasma up and out into the galaxy's sparse outer halo. This process is a key part of something called galactic feedback, a self-regulating cycle that is one of the great balancing acts of the cosmos. The supernova that create the chimneys do two seemingly contradictory things. First, they enrich the space around them by spraying it with newly forged heavy elements, the iron in our blood, the oxygen we breathe, the silicon in rocks. This material, lifted by the chimneys, gets distributed far and wide, seeding future generations of stars and planets with the ingredients for complexity. But second, by violently clearing out gas and heating what remains, these explosions can actually suppress star formation in their immediate vicinity. It is a galactic form of population control. Too many stars born in one place lead to too many supernovae, which then shut down the stellar nursery that created them. The chimneys are the release valve for this pressure. They transport both the energy and the newly minted elements out of the crowded disk, preventing the galaxy from either burning out too quickly or becoming choked with stars. The mystery lies in the precise mechanics. How efficiently do these structures transport material? Do they vent it gently into the halo, or do they fire it out in violent geysers that create giant glowing fountains? Observations suggest our own Milky Way has several of these chimneys, one notably emanating from the bustling star-forming region near the galaxy's center. They are a vivid reminder that a galaxy breathes, that it is an interconnected ecosystem where the death of old stars in one place directly shapes the birth of new ones in another, and ultimately sprinkles the raw materials for planets and life across the vast intergalactic voids. Those giant chimneys scatter enriched material far and wide, but what exactly is that material made of? We often picture interstellar dust as simple, sooty specks, but its true nature is far stranger. This is the fifth mystery, the enigma of interstellar dust composition. For decades, astronomers have known that dust blocks and reddens starlight, but when they analyze its light directly, they find spectral fingerprints that no known substance on Earth can explain. Two sets of these cosmic signatures are particularly baffling. The first appears in infrared light, a set of glowing emission bands that show up around hot stars and in planetary nebulae. They are like a set of distinct musical notes played by the dust when it is warmed by starlight, but we cannot find the instrument that makes them. The second appears in visible light, known as the diffuse interstellar band. When starlight passes through a cloud of dust on its way to our telescopes, hundreds of extremely faint, dark lines are etched into its spectrum. They are absorption lines, meaning something in the cloud is stealing specific colors of that light. Yet, despite a century of searching, we have matched only a handful to any known molecule. The rest remain unidentified, a persistent chorus of spectral lines with no known singer. So what could these mystery materials be? The leading suspects are exotic forms of carbon. One strong candidate is a class of large, stable molecules called polycyclic aromatic hydrocarbons, or PAH. Picture them as tiny, flat flakes, like microscopic pieces of chicken wire made from rings of carbon and hydrogen atoms. They are robust, can survive in harsh space conditions, and their theoretical vibrations match some of the infrared emission bands remarkably well. But they cannot explain all the signatures. Other theorists point to even more novel carbon structures, like tiny cages of carbon atoms known as fullerenes, or long, tangled chains of carbon called carbon nanotubes. Some even speculate about vast, complex organic molecules we have not yet dreamed of in any laboratory. The puzzle is that space seems to be a better chemist than we are, assembling materials under conditions we struggle to replicate. Solving this is not just about identifying a few stray molecules. These dust grains are the raw material for future planets. Their composition dictates what kinds of minerals form, what gases are trapped, and what chemical resources are available when a new solar system coalesces. The diffuse bands and infrared emissions are therefore a direct message from the cosmic foundry, a complex recipe we are still learning to read. Unlocking it would tell us not only what floats between the stars, but what the very bedrock of alien worlds might be made of. These cosmic ingredients, forged in supernova and scattered by chimneys, do not always remain peaceful. Some are hurled across the galaxy at nearly the speed of light, carrying with them an energy that defies belief. This is the sixth mystery, the source of ultra-high-energy cosmic rays. Every second, your body is gently peppered by a rain of atomic fragments from deep space. These are cosmic rays, mostly protons and atomic nuclei stripped of their electrons. Most have modest energies, but a tiny fraction are something else entirely. They possess energies millions of times greater than anything our most powerful particle accelerators, like the Large Hadron Collider, can produce. A single one of these particles carries the kinetic energy of a well-thrown baseball compressed into a subatomic speck. The forces required to accelerate a proton to such a mind-boggling velocity are almost unimaginable. So where in the universe is this natural particle accelerator? The prime suspects are the most violent places we know. Supernova remnants, the expanding shells of debris from exploded stars, have long been a leading candidate. Their chaotic shockwaves could, in theory, act like a vast natural cyclotron, bouncing particles back and forth across the magnetic field until they reach tremendous speeds. Yet, many scientists doubt whether even these titanic explosions are powerful enough to create the very highest energy rays we detect. The search then points to even more monstrous engines. Could they be fired from the vicinities of supermassive black holes at the hearts of active galaxies, where magnetic fields are twisted into cosmic tornadoes and matter is ripped apart? Or perhaps from collisions of entire galaxies, or from mysterious objects we have yet to classify. The central challenge in this detective story is that cosmic rays are charged particles. As they streak across the galaxy, they do not travel in straight lines. The Milky Way's tangled magnetic fields act like a hall of mirrors, bending and twisting their paths endlessly. By the time one of these particles finally strikes Earth's atmosphere, creating a cascade of secondary particles we can detect, all information about its original direction is lost. It is like trying to find the source of a river by examining a single, rain-soaked leaf that has tumbled down 1,000 winding streams. To solve this, astronomers must become indirect detectives. They look for the telltale glow of high-energy gamma rays or neutrinos coming from candidate sources. When a cosmic ray interacts with nearby gas or light, it can produce these secondary messengers which, being neutral, do travel in straight lines. Pinpointing a flood of gamma rays from a supernova remnant, for instance, would be strong evidence that it is indeed a cosmic ray factory. The hunt is ongoing, a global effort using vast detector arrays on the ground and telescopes in space. Each ultra-high-energy cosmic ray that arrives is a postcard from a cosmic catastrophe, but the return address has been scrambled by a galactic magnetic maze. Unlocking their origin would not just identify the universe's most powerful engines, it would reveal the ultimate limits of nature's ability to hatter matter across the void. Those unimaginable energies from cosmic rays hint at a past cataclysm of almost incomprehensible scale, one whose ghostly outline now surrounds us. In 2010, astronomers analyzing data from the Fermi Gamma Ray Space Telescope made a stunning discovery. They found two colossal orbs of high-energy radiation, each one a perfect hemisphere, emerging from the galactic core like a vast hourglass. These are the fermi-bubbles, and they are our seventh mystery. They are not made of stars or glowing gas we can see with our eyes. Instead, they are faint, gargantuan structures revealed only by their emission of gamma rays, the most energetic form of light. Each bubble stretches an astonishing 25,000 light-years from the center of the Milky Way. To grasp their scale, picture our entire solar system as a single grain of sand. On that scale, the bubbles would each be larger than the Earth itself. They are a pair of cosmic bruises, evidence of a titanic outburst that punched a hole in our galaxy's halo sometime in the distant past. The central question is, what was the punch? What event could possibly release enough energy to inflate two bubbles of such staggering size? The prime suspect sits at the very center of the bubbles, our galaxy's supermassive black hole, Sagittarius, a star. While it is quiet today, it may have had a violent past. One leading theory suggests that several million years ago, Sagittarius, a star, experienced a feeding frenzy. As a large cloud of gas or even a star was torn apart and swallowed, The black hole's intense magnetic fields could have funneled some of the infalling material into two powerful opposing jets. These jets, traveling at nearly the speed of light, would have blasted through the galactic halo, heating the thin gas there and creating shock waves that inflated these massive gamma-ray cavities. Another compelling theory points not to the black hole, but to a frenzy of star birth and death. A period of intense star formation in the galactic center could have produced thousands of supernovae in a relatively short cosmic time. Their combined shockwaves and stellar winds might have merged into a single colossal outflow, a superwind powerful enough to blow these giant bubbles. The bubbles' faint, smooth glow and sharp edges offer clues, but they are whispers from an event that ended millions of years ago. Pinpointing the exact trigger and timing is like trying to determine the cause of a forest fire by studying the shape of the ash-covered clearing centuries later. Did the black hole roar to life in a brief, terrifying jet, or was it the coordinated death cries of a generation of massive stars? The answer holds profound implications. If the black hole was responsible, it tells us that even seemingly dormant giants like Sagittarius, a star, can awaken with catastrophic violence, reshaping their entire galaxy in the process. If it was a starburst, it reveals a previously unseen chapter in our galaxy's history, a period of frantic construction and destruction at its heart. The fermi-bubbles are a monument to a forgotten explosion, a reminder that the calm galaxy we see today is just a snapshot in a long, turbulent life. Their silent presence above and below the Milky Way's disk asks us a simple, haunting question. What sleeping dragon did we just discover the breath of? That dragon's breath left a cosmic imprint, but some voids are far closer and far more personal. Just 600 light-years away, floating in front of the glittering band of the Milky Way, lies a patch of sky so profoundly dark it was known to ancient cultures long before telescopes. This is the Coalsack Nebula, a dark nebula in the constellation Crux, the Southern Cross. It appears as a stark, starless hole in the heavens, a perfect blot of ink against the stellar backdrop. Its darkness is not an illusion of distance, it is a tangible object, a massive cloud of cold gas and dust drifting between us and the stars beyond. The mystery of the Coalsack is its profound opacity. Why is it so effective at blotting out starlight? The answer lies in its composition and structure. This is not a uniform sphere, but a complex three-dimensional labyrinth. Think of it as a mountain range made of soot and frozen gas, with peaks and valleys of varying density. The thickest parts are so dense with microscopic dust grains that they absorb virtually all visible light passing through, creating those zones of perfect blackness. Thinner filaments at its edges allow a faint, reddish glow to seep through, as the dust scatters blue light and only lets the longer, red wavelengths pass, a process called interstellar reddening. But what is this cloud's fate, with all that mass estimated to be several thousand times that of our Sun? Gravity should be pulling it inward to form new stars. Yet the Coalsack appears eerily quiet. It is a cold, stable cloud resisting its own collapse. Astronomers believe this stability is maintained by a combination of factors: internal gas pressure, subtle magnetic fields threading through the dust, and likely a significant amount of turbulent motion inside the cloud, like a slow-motion storm that keeps the material stirred up. It is a celestial standoff. The cloud has the raw material to birth stars, but it lacks the final trigger, the external shock wave from a supernova or the collision with another cloud that would overwhelm those supporting forces and tip the balance toward gravity's victory. So for now, the Coalsack sits in suspended animation, a vast dark womb holding its potential in check. It is a reminder that the interstellar medium is not always a frenetic nursery. Sometimes it is a deep freeze, a reservoir of material waiting for the right moment across millions of years to ignite. This silent sentinel of the Southern Cross makes us wonder, is it a future stellar factory or a monument to cosmic stillness? Deep within that same galactic core, another ghostly shape haunts the radio waves. While the Fermi-bubbles glow in high-energy gamma rays, a separate and equally puzzling structure reveals itself in a much quieter voice, the faint crackle of radio emission. This is the galactic center lobe, our ninth mystery, and it paints a different picture of the chaos at the Milky Way's heart. Seen in radio telescopes, it appears as a faint, hourglass-shaped structure, its lobes stretching hundreds of light-years above and below the galactic plane. It is smaller than the colossal Fermi-bubbles but far more intricate, like a delicate twin to those giant orbs. The immediate question is whether these structures are related. They share the same basic orientation and center point, yet they speak in completely different energies. It is as if the same event created two separate echoes, one a thunderous boom of gamma rays, the other a lingering whisper in the radio static. This disconnect is a major clue. The Fermi-bubbles likely trace the aftermath of a violent, short-lived explosion, while the galactic center lobe seems to be shaped by something more persistent, a steady wind or a series of smaller outbursts over a longer time. So what is sculpting this radio hourglass? The theories again point to the two great engines at the galactic center. One possibility is that it is the fossil imprint of an older, less powerful jet from Sagittarius, a star. Perhaps our supermassive black hole has had multiple episodes of activity, not just one giant blast. A slower, more meandering outflow of material from the black hole's vicinity could have inflated these lobes over millions of years, their shape defined by the magnetic fields funneling the material. The other leading theory bypasses the black hole entirely. The very center of the Milky Way is a crowded, frenetic place, home to massive star clusters like the quintuplet and Archer's clusters. These stellar metropolises contain hundreds of scorching young giants. Each one blows off a powerful stellar wind, a continuous stream of charged particles, and they all end their lives as supernovae. The combined effect is a hurricane of energy, a super wind that could constantly blow outward, carving the cavity we see as the lobe and lighting it up with radio waves as the wind slams into the surrounding gas. The mystery deepens with the lobe's remarkable symmetry. How can such a perfect, balanced structure emerge from what should be a chaotic, turbulent environment? It suggests a surprising degree of order, perhaps imposed by a large-scale, organized magnetic field emanating from the galactic center itself, acting as a guide for the outflowing material. Yet, for all our observations, the lobe's exact energy source remains elusive. Is it the fading breath of a black hole's past meal, or the collective shout of a generation of massive stars? Its quiet radio voice holds the answer to a longer, more sustained story of violence at the galaxy's core, a story written not in a single explosive chapter, but across countless stellar lifetimes. The violence at the galactic center forges elements, but some were created in the universe's very first moments, and their numbers simply do not add up. This brings us to the 10th mystery, a flaw in our origin story, the puzzle of interstellar lithium. According to the exquisitely precise theory of Big Bang nucleosynthesis, the first 3 minutes of the cosmos cooked up the primordial elements, vast amounts of hydrogen and helium, and trace amounts of two isotopes, deuterium and lithium-7. The calculations for how much lithium-7 should have been made are robust, grounded in well-understood nuclear physics and confirmed by the accurate predictions for the other elements. Yet, when astronomers look at the oldest stars in our galaxy, stars that formed from nearly pristine gas just after the Big Bang, they find only about 1/3 the amount of lithium-7 the models say should be there. Billions of tons of this primordial element are missing. It is a glaring discrepancy known as the cosmological lithium problem. So where did it go? Could the interstellar medium hold the clues? One possibility is destruction. Perhaps lithium is being broken apart inside those ancient stars themselves. As these old stars churn their internal gases, lithium, which is fragile at stellar temperatures, could be transported to deeper, hotter layers and destroyed. But detailed models of stellar interiors struggle to make this destruction efficient enough to account for the full shortfall. Another avenue points to the space between stars. Could lithium be hiding there, locked away in a form we cannot easily see? Most lithium in the interstellar medium is expected to be in gas form, but if a significant amount has instead condensed onto the surfaces of cold dust grains like frost on a window pane, its spectral signature would be tremendously faint and difficult to detect. Our surveys might simply be missing it because it is not floating freely. There is also the tantalizing, more complex idea that our understanding of the early universe itself is incomplete. Could unknown particles or forces have altered the nuclear reactions in those first 3 minutes? Or perhaps later generations of stars, through poorly understood nuclear processes, produced extra lithium and ejected it, contaminating the medium and confusing our measurements of the primordial baseline. Every new observation seems to deepen the mystery. The Gaia spacecraft, mapping billions of stars, has found that the amount of lithium in similar old stars can vary wildly, suggesting a chaotic history of depletion or enrichment that we do not yet grasp. This is not just a minor accounting error. Lithium-7 is one of the few direct chemical fossils we have from the universe's birth. If we cannot explain its abundance, it means a fundamental chapter of cosmic history is either misunderstood or missing. The interstellar medium is the keeper of that history, a ledger written in elemental abundances. The lithium problem is a single, stubborn entry in that ledger that refuses to balance, whispering that our story of creation, for all its elegance, may still have a crucial page left unturned. Our solar system is not simply drifting through a uniform sea of darkness. We are voyagers inside a vast, invisible cavern. This is the local bubble, a region of space roughly 1,000 light-years across where the interstellar medium is not cold and dense, but eerily hot and incredibly thin. Within this bubble, the gas is a scorching plasma at over 1,000,000 degrees, yet so tenuous that a thimbleful of it would contain only a few atoms. We know this cavity was not always here. It was excavated by a series of titanic explosions, a chain of supernova that detonated in our galactic neighborhood between 10 and 20 million years ago. Imagine a cluster of massive stars living and dying together. Their final, violent blasts would have sent shockwaves plowing through the surrounding gas, sweeping it up into a dense, cool shell and leaving behind this expansive interior of superheated plasma. The mystery lies in the precise history of this ancient catastrophe. How many stars actually exploded? Did they go off in a rapid-fire sequence or over a longer, drawn-out period? The bubble's complex, lumpy shape, mapped by observing the glow of its hot gas in X-rays and the absorption of starlight by its cooler walls, tells a story of a messy, asymmetrical explosion. It is not a perfect sphere, but more like a cosmic froth, with tendrils of hot gas extending in some directions and dense, cold clouds like the famous Taurus molecular cloud pressing against its boundaries. This interaction is a slow-motion cosmic weather front, where the million-degree bubble gas meets frigid cloud material, creating turbulent interfaces and possibly triggering new rounds of star formation in the compressed gas at the edges. The Sun's journey through this local environment is dynamic. We are currently passing through a region within the bubble called the local interstellar cloud, a slightly denser knot of material. In about 50,000 years, we will exit this cloud and move into the even more pristine interior of the bubble itself. This changing neighborhood subtly affects the heliosphere, the protective magnetic bubble blown by the solar wind. The local bubble is our immediate cosmic address, a fossil of ancient stellar violence that cradles our solar system today. Its very existence asks a profound question. Did these same cataclysmic explosions that cleared our space also shower the young Earth with radioactive elements, or even influence the development of life by altering the cosmic rays that reached our planet? We are living inside the aftermath of a forgotten stellar war, and its echoes still shape our voyage through the galaxy. Some voids are not quiet neighbors, they are inbound missiles. High above the plane of the Milky Way, a colossal river of hydrogen gas is screaming toward us. This is the Smith Cloud, a structure 11,000 light-years long and 2,500 light-years wide, containing enough material to forge over 2 million suns. Discovered in the 1960s by astronomy student Gail Smith, its true nature remained obscure for decades. We now know it is hurtling toward our galaxy's disk at nearly 200 miles per second, and in approximately 30 million years it will crash. The mystery is not its trajectory, but its origin. Where did this monstrous cloud come from? One theory paints a tragic picture. It could be the ghost of a failed dwarf galaxy. Perhaps it was a small collection of stars and gas that wandered too close to the Milky Way long ago. Our galaxy's immense gravity could have torn it apart, stripping away its stars and leaving behind only this tattered banner of gas, now falling back in a long, elliptical orbit. Another possibility is that it is a high-velocity cloud, a common feature of the galactic halo. These clouds are thought to be the condensed, raining down remnants of the primordial gas that formed the galaxy, or material expelled by the fermi-bubbles and now cooling and falling back. Yet the Smith Cloud is different. Its metallicity, the amount of heavy elements within it, holds a crucial clue. Recent observations show it contains sulfur and other elements in amounts similar to the outer disk of the Milky Way. This suggests it is not pristine, primordial gas, but material that has already been processed inside stars. This points to a dramatic third origin. It could be a giant plume of gas that was violently ripped out of the Milky Way's own disk during a close encounter with another galaxy billions of years ago, flung high into the halo, and is now completing its terrible arc back home. So the Smith Cloud is likely not an invader, but a prodigal son returning after an epic multi-billion-year journey. Its impending collision is not a catastrophe, but a delivery. When it slams into the galactic plane, the impact will be a slow-motion, continent-scale collision of gases. The cloud will compress the existing interstellar medium, and its own vast reservoir of hydrogen will be squeezed by tremendous shockwaves. In the dense, turbulent knots that form, gravity will finally take hold. The result is predicted to be a firestorm of star birth, a spectacular stellar nursery spanning thousands of light years, glowing with the blue light of newborn massive stars. It will be a cosmic renaissance, a burst of creation triggered by a returning ghost. This event will enrich a region of our galaxy with fresh fuel and likely seed new planetary systems. The Smith Cloud's journey reminds us that a galaxy is not a closed system. It is an active, breathing entity that sometimes consumes its own expelled material, turning its past ejecta into the seeds of its future. But that faint radio whisper is just one layer of a deeper, more pervasive static. Across the entire sky, there is a faint, enigmatic glow that has nothing to do with stars or galaxies. It is called the anomalous microwave emission, a mysterious signal that first appeared as an unaccounted-for haze in maps of the cosmos. For years, astronomers meticulously charted the sky's microwave light, the gentle afterglow of the Big Bang known as the cosmic microwave background. To see that pristine fossil, they had to subtract all the foreground contamination, the glow of our own galaxy's dust and gas. Yet, no matter how carefully they subtracted the known sources, a diffuse, patchy emission stubbornly remained. It was a ghost in the machine, a faint hiss that did not belong. The initial suspect was something called spinning dust. Picture a microscopic grain of interstellar dust, not much larger than a molecule. When it is hit by a single ultraviolet photon or struck by a passing atom, it can be set spinning at dizzying speeds, billions of rotations per second. A spinning electric dipole, no matter how tiny, emits radiation. For these nanoparticles, that radiation falls right in the microwave part of the spectrum. It was a beautiful, elegant explanation, but as observations improved, a problem emerged. The detailed shape of this anomalous emission spectrum, the specific fingerprint of its light, did not perfectly match the predictions for spinning dust grains. It was close, tantalizingly close, but something was off. The ghost had a slightly different face than expected, so the detective work intensified. If not simple spinning dust, what could it be? One compelling alternative involves not just spin, but magnetism. What if the carriers are not just dust grains, but nanoparticles of iron or other magnetic materials? The theory suggests these could be super-paramagnetic grains. Their internal magnetic fields could fluctuate wildly, and as they align with the galaxy's magnetic field, that interaction could release energy as microwave radiation. This process would produce a slightly different spectral signature, one that might solve the mismatch. Another, more exotic idea points to a specific, large molecule, polycyclic aromatic hydrocarbons. These flat plates of carbon and hydrogen could not only produce the infrared emission bands we discussed earlier, but when they are charged up and spinning, they might also contribute to this anomalous microwave glow. The challenge is that we are trying to identify the behavior of particles we cannot directly see, using only the faint whisper of their collective radio choir. Why does this obscure signal matter so much? Its importance cannot be overstated, because it is a source of noise in the most important cosmological observation we have, the cosmic microwave background. That ancient light is our baby picture of the universe, and from its subtle imperfections we have deduced the age, composition, and evolution of everything. To see those imperfections clearly, we must remove every speck of foreground contamination with absolute precision. The anomalous microwave emission is like a faint fog lying between us and that primordial photograph. If we misidentify its source or miscalculate its intensity, we risk misinterpreting the patterns in the cosmic microwave background itself. A small error in cleaning the fog could lead to a massive error in understanding the universe's fundamental ingredients, like the amounts of dark matter and dark energy. So this faint galactic haze is more than a curiosity. It is a barrier to cosmic clarity. Unlocking its origin is the final step in wiping the dust from our window to the beginning of time, ensuring we are seeing the true face of creation and not a trick of the interstellar medium. The faint microwave haze is a veil over the cosmos, but other structures scream their presence across a different part of the spectrum. In 2019, the Milky-way radio telescope in South Africa peered at the heart of our galaxy and saw something that defied simple description. Stretching from the galactic core were two colossal, symmetrical plumes of magnetized energy, each one reaching over 1,300 light-years into space. They are not the gamma-ray fermi-bubbles nor the delicate radio hourglass of the galactic center lobe. These are the galactic geysers of Milky-way, and they are our 14th mystery. Imagine a pair of vast hourglass-shaped fountains, but instead of water, they are twin jets of relativistic particles and tangled magnetic fields glowing fiercely in radio light. They are narrower and more focused than the enormous fermi-bubbles, yet far larger and more energetic than the galactic center lobe. This discovery presented astronomers with a stunning layered architecture at the Milky Way's core. The giant gamma-ray fermi-bubbles form the outermost shell. Within them, these newly found radio geysers create a distinct inner structure, and at the very center lies the intricate hourglass of the galactic center lobe. It is a cosmic Russian doll of violent history. The leading theory is that all these structures are linked to a single cataclysmic event, a phenomenally energetic outburst from our supermassive black hole, Sagittarius, a star that occurred roughly 3.5 million years ago. This was not a gentle awakening. The black hole likely experienced a sudden, enormous influx of material, perhaps a star or a massive gas cloud torn apart by its gravity. As matter spiraled into the abyss, intense magnetic fields near the event horizon funneled some of it into two opposing, pencil-thin jets traveling at a significant fraction of light speed. These jets, focused and unimaginably powerful, punched through the surrounding gas, inflating the radio geysers we see today. Their energy then continued to propagate outward, creating the shockwaves that later inflated the larger, slower-moving fermi-bubbles. The implications for galactic ecology are profound. This event was not just a spectacle, it was a transformative episode for our entire galaxy. The geysers and bubbles act as a colossal feedback mechanism. The energy they injected into the galactic halo would have heated the sparse gas there, preventing it from cooling and falling back into the disk to form new stars. This effectively put a cap on star formation in the Milky Way's central regions for millions of years. Furthermore, the jets would have carried heavy elements forged in stellar explosions near the black hole and sprayed them far into the galactic halo, chemically enriching territories that had never known such materials. It means the black hole, in a single violent tantrum, helped regulate the galaxy's growth and redistributed the seeds of planets and life across vast distances. The Milky-way geysers are thus a fossilized snapshot of that tantrum, a direct imprint of the black hole's focused power. They force us to see Sagittarius, a star, not as a dormant pit, but as a sleeping volcano with a violent and recent history, capable of reaching out and touching the galaxy that surrounds it with jets of pure energy. That black hole's violent tantrum scattered energy across the galaxy, but some corners of space achieve a profound stillness that defies the universe's own warmth. Drifting 5,000 light-years away in the constellation Centaurus is a ghostly bow tie of gas known as the Boomerang Nebula. It holds a chilling title, the coldest natural place we have ever found. Measurements from telescopes like the Atacama Large Millimeter Array reveal its temperature is a mere 1 degree above absolute zero, a fraction of a Kelvin colder than even the cosmic microwave background radiation, the leftover warmth from the Big Bang itself. This nebula is not just cold, it is actively colder than the residual heat of creation. The principle behind this deep freeze is a familiar one: expansion. Just as a spray can get cold when you release the pressurized gas inside, the Boomerang Nebula is undergoing a rapid, catastrophic expansion. It is the death shroud of a central red giant star, now in its final transformation into a white dwarf. This dying star is losing mass at a staggering rate, ejecting its outer layers in a fierce stellar wind moving at over 160 kilometers per second. As this gas billows outward into the near-perfect vacuum of space, it expands violently and adiabatically, meaning it does so without gaining any heat from its surroundings. The molecules in the gas must use their own internal thermal energy to fuel that expansion, and as they do, their motion slows to a crawl, plunging the temperature to that record-breaking low. The mystery, however, is not just the cold but the shape. Why does this expanding cloud form a distinct, asymmetrical hourglass, a nearly perfect boomerang? Simple spherical expansion would not create such a form. The answer likely lies in the central star's past. Many astronomers believe the star at the heart of the nebula was once part of a binary system. As it entered its death throes, it may have consumed or violently interacted with its companion. That gravitational dance could have funneled the ejected material into a dense disk of dust and gas around the star's equator. The fastest, most energetic outflow then escapes perpendicular to this disk, punching out along the star's poles and creating the two opposing lobes we see. The denser equatorial disk acts like a waistband, cinching the expanding cloud into its distinctive double-lobed or bipolar shape. Yet, the precise physics that allows it to reach temperatures lower than the cosmic microwave background remains an active puzzle. It suggests the expansion is not just fast, but incredibly efficient and uniform, with the gas managing to avoid any significant heating from starlight, interstellar radiation, or shock waves within itself. This nebula is a natural laboratory for extreme thermodynamics, showing us how the death of a star can create a pocket of space that, for a brief cosmic moment, is colder than the universe itself. It makes us wonder what other extreme environments are being sculpted by dying stars, and what their final, frozen forms can teach us about the ultimate fate of matter. That profound cold is a testament to the intricate chemistry of the void, a chemistry that leaves its signature in stolen starlight. For over a century, astronomers have been haunted by a ghostly fingerprint in the light of distant stars. When they split that light into a rainbow spectrum, they find not just the expected dark lines from known atoms, but hundreds of additional, extremely faint absorption lines. No known substance on Earth produces them. These are the diffuse interstellar bands, and they are one of the oldest and most stubborn mysteries in all of astrophysics. Think of starlight as a pure, white beam of information traveling across space. When it passes through a cloud of interstellar material, specific colors are absorbed by atoms and molecules in that cloud, creating dark gaps in the spectrum. We can read those gaps like a barcode, identifying hydrogen, helium, calcium, and more. But superimposed on that familiar barcode are these extra lines, over 500 of them, that simply do not match anything in our terrestrial libraries. They are diffuse, meaning they are broad and fuzzy, not sharp like atomic lines, which tells us they are not coming from simple atoms or small molecules. They are the signature of something much larger and more complex. The hunt for the culprit has been a century-long detective story, and all clues point to the dark, organic chemistry of the interstellar medium. The most promising suspects are large, carbon-based molecules, the so-called macromolecules of space. These could be sprawling chains of carbon atoms like polyions, or vast, cage-like structures known as fullerenes, or even the flat, plate-like polycyclic aromatic hydrocarbons we've met before. Their size and structure would explain the broad, diffuse nature of the bands. Large molecules have many more ways to vibrate and rotate, smearing their absorption signature across a wider range of colors. Imagine trying to identify a person not by a single, clear photograph, but by the combined, blurry shadow of their entire family standing together. That is the challenge of the diffuse bands. Why has it been so difficult to crack this case? The problem is one of scale and environment. These molecules are likely produced in the harsh conditions of space, in the cool outflows of dying stars, or on the surfaces of dust grains, conditions incredibly difficult to replicate perfectly in a laboratory on Earth. Furthermore, a single band might not belong to one molecule, but to a whole family of similar ones, their individual signals blending into a single, unresolved line. It is a cosmic mixture of fingerprints all overlaid. Solving the diabese is far more than an academic exercise. It is the key to reading the complete chemical inventory of the interstellar medium. These bands are the direct spectral evidence of the most complex chemistry occurring in the vast darkness between stars. By identifying the molecules that cause them, we would know exactly what kinds of organic materials are being manufactured out there. This is the feedstock for new solar systems. Were these complex carbon molecules delivered to the early Earth? Do they rain down on exoplanets in other star systems, providing a head start for chemistry that could lead to life? The diffuse bands are the hidden catalog of that cosmic delivery service. Every time we look at a star and see those faint, dark lines, we are seeing the shadow of complexity itself, a chemical richness in the void that we are only beginning to decode. Unlocking their identity would finally tell us what the universe is using as its building blocks for everything that comes next. But those ghostly spectral lines are not the only mysterious signatures written across our sky. High above the plane of the Milky Way, arching across the constellation of Scorpius and into Lupus, is a colossal structure of glowing gas that dominates the northern galactic hemisphere. This is the North Polar Spur, a vast arc of radio and X-ray emission so immense it spans over 120 degrees of the sky. From our perspective on Earth, it appears as a giant, faint band of energy, like a celestial rainbow painted in the invisible light of high-energy physics. Its sheer size and brightness make it one of the most prominent features in the entire radio sky, yet for decades, its true nature has been a subject of intense debate. The core of the mystery is deceptively simple. How far away is it? Is it a local landmark in our galactic neighborhood, or a distant monument on the scale of the galaxy itself? Each possibility paints a dramatically different picture of its origin. The first theory argues it is a nearby supernova remnant. If the spur is relatively close, perhaps only a few hundred light-years away, then it could be the expanding shell of a single titanic stellar explosion that occurred within the last 100,000 years. Its bright, filamentary structure would then be the shockwave from that blast, plowing through the local interstellar medium and lighting it up. This would make it a spectacular, albeit fading, testament to a recent cataclysm right in our cosmic backyard. A second, closely related idea connects it directly to our local bubble. Could the spur be part of the shock front or the energized wall of that million-degree cavity we live inside? Perhaps it is not from one supernova, but the combined, rippling aftermath of the multiple explosions that carved out our bubble, a persistent scar on the sky from the ancient violence that cleared our region of space. Yet a third and equally compelling theory places it much, much farther away. What if the North Polar Spur is not local at all, but a distant structure hundreds or even thousands of light years from Earth, possibly connected to the fermi-bubbles or other activity emanating from the galactic center? At that distance, its immense apparent size would translate to a truly gargantuan physical scale, rivaling some of the largest structures in the Milky Way. This interpretation suggests it might be a magnetic filament or a vast shockwave in the galactic halo, a piece of the galaxy's large-scale weather system. The problem is one of cosmic parallax. For objects within our galaxy, determining distance is often done by measuring their motion against the background or by finding associated stars with known distances. But the North Polar Spur is diffuse and complex. It has no clear stellar engine or crisp boundary to latch onto. It is like trying to judge the distance to a mountain range seen through thick fog. Is it a small, nearby ridge or a massive, distant chain? Its proximity is what makes it so brilliantly visible to our telescopes, but that same brightness ironically makes it harder to interpret. A nearby object would be physically smaller and less energetic, while a distant one must be unimaginably large and powerful to appear so bright. Recent observations from X-ray telescopes like eROSITA are adding new pieces to the puzzle, mapping the spur's hot gas in exquisite detail and suggesting it may be connected to other large-scale structures in the galactic halo. The debate continues, a testament to the fundamental challenge of mapping a three-dimensional universe from our single, fixed vantage point. The North Polar Spur hangs above us, a luminous question mark in the sky, asking us to decide if we are looking at the fading echo of a nearby star's death or the distant roar of the galaxy's own mighty engines. That profound cold is where the most fundamental bond in the universe must somehow take hold. Molecular hydrogen, two hydrogen atoms bound together, is the primary fuel for star formation. It is the molecule that fills the vast clouds where gravity first gains its foothold. Yet, forming this simple pair in the vacuum of space presents a paradox that puzzled scientists for generations. The problem is one of pure physics. In the near-perfect emptiness of the interstellar medium, two lone hydrogen atoms speeding toward each other will meet, but they cannot simply stick. When they collide, they would naturally form a temporary, unstable molecule. But that bond releases a burst of energy, and with nothing else to absorb that energy, the molecule immediately vibrates itself apart. It is like trying to glue two perfectly smooth, wet marbles together. They touch, but without something to hold them in place as the adhesive sets, they just roll away. So how does the cosmos solve this? The answer is a cosmic matchmaker, a third body that is absolutely everywhere, the surface of an interstellar dust grain. These microscopic particles, mere flecks of silicate or carbon, provide the crucial platform. A single hydrogen atom drifting through the cold of a dark nebula will eventually strike a dust grain and stick to its surface, held by weak chemical forces. It is not alone for long. Another hydrogen atom lands nearby. Now, instead of colliding in open space, they are both immobilized on the same tiny platform. They can slide across the grain's surface, a process called diffusion, until they eventually find each other. When they meet on the grain, they can form that bond. This time, the energy released by the bond formation is immediately absorbed by the entire lattice structure of the dust grain itself. The grain acts as a shock absorber, taking that vibrational energy and dissipating it, allowing the newly formed hydrogen molecule to remain stable. Once formed, the weak forces holding it to the grain are easily overcome by the bond's own energy or by another incoming particle, and the molecule is released back into the gas, ready to contribute to a future star-forming cloud. This process, known as surface-mediated recombination, is the dominant way molecular hydrogen forms in the universe, but confirming this elegant theory has been a monumental challenge. It requires recreating the extreme conditions of interstellar space in a laboratory ultra-high vacuums, temperatures just a few degrees above absolute zero, and pristine surfaces. Scientists use sophisticated machines to simulate the slow dance of atoms on artificial dust grains, watching for the telltale signature of a hydrogen molecule popping free. In space, the evidence is indirect but compelling. By observing the ratio of atomic to molecular hydrogen in different environments, from the diffuse, ultraviolet-bathed regions to the shielded hearts of dark clouds, astronomers can map where this surface chemistry is most efficient. The mystery now lies in the nuances. How does the composition of the dust grain, whether it is carbon-rich or silicate, affect the efficiency? What role do the grain's imperfections and icy coatings play? Even the gentlest cosmic radiation or the faintest heat from a distant star could alter the delicate waltz happening on these microscopic stages. Understanding this process is not a minor detail. It is the study of the first step in the cosmic cycle of creation. Without molecular hydrogen, there are no cold, dense clouds. Without those clouds, there is no star formation. Without stars, there are no heavy elements, no planets, and no life. Those tiny, cold grains of dust are therefore the unsung midwives of the cosmos, facilitating the very first bond upon which all future structures depend. Every star you see began with a silent, microscopic meeting on a speck of dust in the dark. Our galactic neighborhood is dotted with the ghosts of ancient cataclysms. Scattered across the radio sky are three immense, faint shells, each one a perfect, nearly circular arc of synchrotron emission. These are the galactic radio loops, most famously known as Loop 1, 2, and 3. They are colossal structures, with Loop 1, also called the North Polar Spur, stretching over 100 degrees across the sky. Their smooth, shell-like shape is the classic signature of a supernova remnant, the expanding shockwave from a star's final, violent explosion. These loops are not active, chaotic nebulae like the Crab. They are old and fading, their energy spread thin across vast volumes. They are the lingering echoes of stellar deaths that occurred tens or even hundreds of thousands of years ago, right in our own cosmic backyard. The central mystery is not what they are, but precisely where and when they happened. Determining the distance to a faint, diffuse radio shell is notoriously difficult. Without a clear, compact central source like a pulsar to pinpoint, astronomers must rely on indirect clues. They study how the loop's radio emission interacts with or obscures known clouds of interstellar gas at various distances. They look for faint X-ray counterparts that might reveal million-degree gas inside the shell. They even analyze the polarization of the radio waves, which traces magnetic fields compressed by the shock wave to map its three-dimensional structure. Each loop tells a separate story of a different explosion. Loop 1, the largest and brightest, is likely the remnant of a supernova that erupted between 100 and 1,000 light-years away, perhaps within the SCO-Centaurus stellar association. Its immense size suggests it is quite old, its shock wave having traveled for nearly 1 million years through the low-density cavity of our local bubble. Loop 3 is smaller and fainter, possibly the relic of a more recent but more distant explosion. The ultimate goal is to connect each radio loop to its progenitor star. What kind of star met its end to create such a perfect spherical shell? Was it a massive, short-lived blue giant or an elderly white dwarf that stole too much material from a companion and detonated? Finding that stellar corpse, a neutron star or black hole somewhere near the loop's geometric center, would be the smoking gun. But after so many millennia, any remnant has had ample time to drift away from the epicenter, kicked by the asymmetrical force of the explosion itself. Piecing together this history is like forensic archaeology on a galactic scale. By mapping the loop's sizes, expansion speeds, and the material they are plowing into, astronomers can rewind the cosmic clock. They can estimate not only when each star died, but also how much energy was released and what heavy elements were forged in the blast and sprayed into the local interstellar medium. These loops are more than just fossils, they are active participants in shaping our environment. Their expanding shock waves continue to compress nearby clouds of gas, potentially triggering new rounds of star formation. They have also likely contributed to the turbulent, frothy structure of the local bubble we reside in. Every one of these faint radio rings is a chapter in the biography of our galactic neighborhood, a record of how the violent deaths of nearby stars have repeatedly swept, enriched, and reshaped the space around our solar system over the eons. Their silent glow asks us to consider our own place within an ever-changing landscape, one sculpted by ancient explosions whose light reached Earth long before humans walked its surface. Those faint radio rings are local echoes, but the early universe held structures of such scale they defy modern comparison. Drifting in the cosmic dawn over 11 billion light-years away are the Lyman alpha blobs. These are not galaxies, but colossal clouds of primordial hydrogen gas, each one spanning hundreds of thousands of light-years, far larger than the entire Milky Way. They are named for the specific shade of ultraviolet light they emit, the Lyman alpha line, which is the fingerprint of a hydrogen atom releasing energy. But that simple fingerprint creates a profound mystery. Why are these gargantuan clouds glowing so fiercely? A cloud of hydrogen in empty space should be dark and cold. For it to shine, something must be energizing it, pumping it full of power on an almost unimaginable scale. Astronomers have proposed 3 possible engines, each one a titanic force in the young cosmos. The first is a frenzy of creation. Perhaps the blob is the site of the universe's first giant starburst, a hidden metropolis where stars are being born at a rate thousands of times faster than in our galaxy today. The intense ultraviolet light from all those newborn, massive stars would ionize the surrounding hydrogen, causing it to glow in that characteristic Lyman alpha light as it recombined. The blob would then be a vast, luminous nursery, its glow the combined birth cry of countless suns. The second possibility is more violent. At the heart of the blob could lie a voracious supermassive black hole, a quasar in its youth. As vast rivers of gas spiral into this gravitational abyss, the material is heated to millions of degrees, blazing with radiation before it vanishes. This incredible flood of energy could be illuminating the entire surrounding cloud, like a single, brilliant lighthouse flooding a whole fog bank with light. The third idea is subtler but equally dramatic. The glow could be the heat of formation itself. As the blob, a massive knot in the cosmic web, draws in fresh gas from the filaments around it, that gas falls inward at tremendous speeds. The gravitational energy of this infalling material is converted into heat and light as it crashes into the cloud's core, causing it to shine from the sheer violence of its own growth. The truth is, these mechanisms likely work together. Observations with telescopes like the Subaru and the Very Large Telescope show that many blobs do contain intense star-forming regions or hidden quasars. Yet, the glow often extends far beyond these central engines, suggesting a more complex story where all these processes, stellar birth, black hole feeding, and cosmic accretion combine to light up these primordial behemoths. Their significance cannot be overstated. Lyman alpha blobs are likely the precursors to the most massive galaxies and galaxy clusters we see today. They represent a critical phase when the first giant structures were pulling themselves together from the raw hydrogen of the early universe, lighting their way with the very first bursts of energetic astrophysics. To study a blob is to watch a galaxy cluster under construction in the cosmic dawn, to see the scaffolding of the large-scale universe being assembled and set aglow by the furious processes of creation happening within. High above the galactic plane, a silent rain is falling. Streaking through the halo of the Milky Way are enormous, fast-moving clouds of cold hydrogen gas, some as massive as 1,000,000 suns. These are the high-velocity clouds, and their very existence challenges our understanding of how a galaxy breathes. They are not orbiting gracefully with the rest of the galactic disk. Instead, they are plunging inward or streaming outward at velocities hundreds of kilometers per second faster than the simple rotation of the Milky Way would allow. They are celestial mavericks, and their origin story is a key piece of the galaxy's ongoing evolution. So where do these speedy giants come from? Astronomers see three compelling and possibly interwoven narratives. The first is a story of ancient leftovers. These clouds could be primordial relics, pockets of the pristine hydrogen and helium gas that never fully collapsed into the galactic disk during the Milky Way's formation billions of years ago. They have been swirling in the vast halo ever since, a fossilized rain that never quite fell, now finally beginning its long-delayed descent. The second narrative is one of galactic cannibalism. Our Milky Way has a history of consuming smaller satellite galaxies. As these dwarf galaxies are torn apart by tidal forces, their stars are stripped away into long streams, but so is their gas. A high-velocity cloud could be the tattered, gaseous shreds of such a devoured companion, a ghost of a galaxy now falling back toward its destroyer. The third possibility is a cycle of galactic fountain and condensation. Remember the fermi-bubbles and galactic chimneys. They blow hot, enriched gas out of the disk and into the halo. That gas, as it travels far from the energetic heart of the galaxy, might eventually cool, condense, and clump together into these massive clouds of neutral hydrogen. Under the pull of gravity, they would then turn around and fall back toward the disk, completing the cycle. This would make them not invaders or fossils, but recycled material, the galaxy reusing its own exhaust. The evidence lies in their composition. By analyzing the faint light of distant quasars shining through these clouds, astronomers can detect trace amounts of heavy elements. Some clouds show very low metallicity, hinting at a primordial origin. Others have compositions more similar to the Milky Way's outer disk, supporting the galactic fountain model. The Smith cloud we discussed earlier is a prime example of a high-velocity cloud with a metallicity that suggests it was ripped from our own galaxy long ago. Regardless of their precise origin, their destiny is profound. These clouds represent a vital source of fresh fuel. As they crash into the thinner gas of the galactic plane, their immense mass compresses the interstellar medium. This compression can trigger gravitational collapse, igniting new waves of star formation. They are the galactic rainfall, delivering the cold, dense hydrogen necessary to build future generations of suns. Without this constant, if sporadic, infusion of new material from the halo, the Milky Way's star-forming factories might eventually run dry. The high-velocity clouds are thus a critical part of the galaxy's long-term metabolism. They are the mechanism by which a galaxy gathers its dispersed resources, drawing from its own extended atmosphere to feed continued growth and renewal in the bustling disk below. Their silent, high-speed trajectories trace the grand, slow-motion weather patterns of an entire galaxy, a forecast predicting where the next burst of stellar light will one day shine. Just 500 light-years from Earth, a sprawling tapestry of dust and gas drifts through the constellation of the Serpent Bearer. This is the Ophiuchus dark cloud complex, one of the nearest and most active stellar nurseries to our solar system. Within its shadowy folds, the brilliant blue reflection nebula around the star row Ophiuchi shines like a beacon, a region where suns are being born right now. Yet this vast complex presents a striking puzzle. Why are some sections, like the Rho Ophiuchi region, ablaze with the light of young stars, while other patches of seemingly identical, cold dark cloud lie in perfect stillness, holding their potential in check? It is a cosmic case of nature versus nurture on an interstellar scale, where the fate of a cloud hinges on a delicate balance of internal fortitude and external chaos. The difference lies in the triggers. A dark cloud, no matter how massive, can resist its own gravitational collapse for millions of years. Internal gas pressure, subtle turbulence, and especially magnetic fields create a supporting structure, like a scaffold holding up a building. For star formation to begin, something must overwhelm that support. In the active regions of Ophiuchus, astronomers see the fingerprints of powerful external shocks. The complex is not isolated. It sits within a bustling galactic neighborhood. The shock wave from a nearby supernova that exploded long ago could have slammed into one section of the cloud, compressing the gas and dust into dense, gravitationally unstable knots. Alternatively, the intense radiation and stellar winds from massive, hot stars already born on the cloud's outskirts, stars like those in the Scorpius-Centaurus association, could be acting like a cosmic plow. Their relentless pressure squeezes the cloud's surface, driving compression waves deep into its interior and initiating collapse in a process called radiation-driven implosion. The active Rho Ophiuchi region is likely a beneficiary of such external violence, its star formation sparked by the tumultuous environment around it. But what of the quiet zones? These are regions that have, so far, avoided a direct hit. They possess the same raw material, the same density, but their internal supporting forces remain unchallenged. Here, the strength of the magnetic field threading through the cloud becomes the decisive factor. Imagine the cloud's gas is threaded with invisible magnetic lines, like iron filings around a bar magnet. These lines exert a pressure, resisting any motion that tries to compress the cloud across them. In a region with a particularly strong, ordered magnetic field, this support can be formidable, preventing the cloud from fragmenting into the dense cores that become stars. The cloud's own internal turbulence also plays a dual role. While it can sometimes create density enhancements that lead to collapse, it can also provide a form of pressure that helps the cloud maintain its equilibrium, a constant churning that prevents any single region from becoming unstable. The Ophiuchus cloud complex is therefore a living laboratory displaying every stage of stellar gestation. In one quadrant, a shock front has passed, leaving behind a cascade of collapsing cores and newborn protostars still wrapped in their dusty cocoons. In another, a strong magnetic field maintains a serene, if tense, peace. And in yet another, the slow diffusion of magnetic fields, a process called ambipolar diffusion, where neutral gas slips past the charged particles tied to magnetic lines, might be quietly weakening the scaffold, setting the stage for a future collapse without any external trigger at all. This patchwork of activity shows us that star formation is not a uniform process that happens everywhere at once. It is a sporadic, almost contagious phenomenon, ignited by specific local conditions. The quiet parts of the cloud are not failed nurseries, they are reservoirs waiting for the right push at the right time. Their silence today is the prelude to a storm of creation that may ignite tomorrow, or in a million years, reminding us that even in the darkness, the potential for light is always present, held in suspense by invisible forces. Threading through that chaotic tapestry of clouds and voids is an invisible architecture of unimaginable scale. The Milky Way is not just a collection of stars and gas, it is a magnetized galaxy. A vast, coherent magnetic field permeates the entire disk, its lines weaving through the spiral arms and stretching far into the halo. We can map its presence by observing the subtle polarization of starlight, which dust grains align along the field lines, and by the faint radio glow from electrons spiraling around these cosmic threads. But this discovery leads directly to a profound mystery. Where did this galactic magnet come from in the first place? The leading explanation is a process of cosmic amplification known as the galactic dynamo. Picture the galaxy as a vast, slow-moving engine. Its differential rotation, the inner parts spinning faster than the outer parts, acts like a great cosmic spindle. It takes any weak, pre-existing magnetic field and stretches it, pulling it into long, coherent lines that wrap around the galactic center. Meanwhile, the violent turbulence within the interstellar medium, the churning from supernova, stellar winds, and cloud collisions twists and tangles those lines. This combination of stretching and twisting can, in theory, amplify a weak seed field into the organized, large-scale structure we observe today. It is a self-sustaining cycle where the motion of the charged gas generates more magnetic field, which in turn influences the motion of the gas. The dynamo theory is elegant, but it rests on a critical and unresolved assumption. It requires a seed. You cannot amplify a magnetic field from zero. There must have been a tiny, primordial magnetic field present in the early universe to kickstart the entire process. And here we hit the first great wall of this mystery. What was the origin of that initial seed field? Was it generated in the unimaginable violence of the Big Bang itself, a relic woven into the fabric of space-time? Or did it emerge later, perhaps from the first generation of stars and galaxies, whose intense radiation and turbulent outflows could have created localized magnetic fields that then spread? Some theories even point to the universe's earliest moments, suggesting that phase transitions in the seething quantum foam of the infant cosmos could have generated these first magnetic whispers. We simply do not know. This seed field would have been astonishingly weak, perhaps a billion times fainter than Earth's own magnetic field. Yet, over billions of years of galactic rotation and turbulence, the dynamo could have amplified it to its present strength. But the mystery deepens when we consider the field's influence on the very stuff of creation. How do these galaxy-spanning magnetic fields affect the collapse of clouds to form stars? They are not passive spectators. Within a dark nebula, magnetic fields provide a crucial form of support, acting like a scaffold of invisible wires that holds the cloud up against its own gravity. For a star to be born, this support must be overcome. The prevailing theory is a slow, patient process called ambipolar diffusion. In a molecular cloud, the magnetic field is effectively frozen into the ionized, charged particles, the tiny fraction of gas that is electrically conductive. The vast majority of the cloud, however, is neutral hydrogen molecules. The charged particles are locked to the magnetic field lines and cannot move across them, but the neutral gas can. Over millions of years, the neutral gas slowly drifts or diffuses through this stationary magnetic scaffold, pooling in the densest regions. Gradually, enough mass gathers in one place that gravity finally overwhelms the weakened magnetic support in that specific knot, and collapse begins. It is a cosmic act of patience where the magnetic field dictates the pace and the location of star birth. In some cases, the field can even channel the collapsing material, funneling it along its lines and influencing the rotation of the nascent protostar and the formation of its eventual planetary disk. The galactic magnetic field is thus both an architect and a regulator. It may have grown from a faint, mysterious seed in the dawn of time, and now it silently guides the process of stellar genesis, shaping where and when new suns ignite in the dark. To understand the full story of our galaxy's formation and continued evolution, we must first trace the origin of this invisible, pervasive force that binds the chaos together. The southern sky holds a ghost so vast it defies comprehension. Stretching across the constellations of Vela and Puppis is the Gum Nebula, an enormous shell of faintly glowing gas that spans a staggering 40 degrees of the sky. If it were bright enough, it would appear larger than 80 full moons lined up side by side. Its true physical size is even more breathtaking, over 1,000 light-years in diameter, making it one of the largest single structures in our entire galactic neighborhood. This nebula is a whisper, a pale, diffuse veil of hydrogen gas excited to a gentle red glow, so faint it was only discovered in the 1950s. Its very existence poses a monumental puzzle. How could something this enormous be created? The leading theory points to a cataclysm of almost unimaginable scale. The Gum Nebula is believed to be the fossilized remnant of a supernova, or perhaps a series of supernovae that detonated over 1 million years ago. But a single, typical supernova remnant, like the famous Crab Nebula, is only about 10 light-years across. To inflate a bubble 1,000 light-years wide would require an explosion of staggering energy, or a sustained series of blasts acting in concert over millennia. The mystery deepens when we look at its contents. Embedded within the Gum Nebula's faint embrace are two other famous objects that seem to tell pieces of the same violent story. At its heart lies the Vela supernova remnant, the much younger, brighter, and more compact debris from a star that exploded a mere 11,000 years ago. It is like finding a fresh, still smoking crater inside the boundaries of a vast, ancient impact basin. Then there is Zeta Puppis, also known as NOWS, a brilliant blue runaway star blazing with the intensity of 20,000 suns. Spectroscopic analysis shows it is hurtling through space, and if we trace its path backwards, it appears to have been ejected from the region of the Vela remnant. This paints a compelling, chaotic picture of overlapping stellar deaths. Perhaps the story began over 1 million years ago in a crowded stellar cluster. One massive star reached the end of its life and exploded, its shockwave beginning to carve out the colossal cavity we now call the Gum Nebula. That first explosion may have triggered the collapse of nearby clouds, spurring the birth of new, massive stars, including the progenitor of the Vela supernova and Zeta Puppis. Then, just 11,000 years ago, the Vela star itself exploded. That more recent cataclysm likely gave Zeta Puppis a tremendous gravitational kick, sending it racing away like a cosmic bullet, while also adding its energy to the ongoing expansion of the larger Gum shell. So the Gum Nebula may not be the relic of one event, but a palimpsest of violence, a layered fossil record where the death screams of multiple giant stars have merged over eons into a single, faint, and gigantic echo. It is a celestial archaeology site where we must decipher the sequence of explosions that sculpted our local space, reminding us that even the quietest corners of the sky can hold memories of titanic, overlapping catastrophes. Even the faintest whispers can reveal a hidden storm. Deep within the Sword of Orion, in the brilliant glow of the stellar nursery known as the Orion Nebula, lies a sharp, glowing ridge called the Orion Bar. This is not a solid structure, but a violent frontier, a photodissociation region where the fierce ultraviolet light from newborn, massive stars slams into a wall of cold molecular gas. It is here, in this chaotic interface of light and shadow, that astronomers stumbled upon a chemical anomaly. They detected far more of a simple ion, called methylidine ion or CH+, than any standard model of interstellar chemistry could account for. This is not just a missing molecule, it is a molecule that should not exist here in such abundance. CH+ is a fragile ion, a simple pairing of a carbon atom and a hydrogen atom that carries a positive charge. In the cold, quiet depths of a dark cloud, it is easily destroyed. To form it in significant quantities requires either extremely high temperatures, around 1000 degrees Kelvin, or a tremendous injection of turbulent kinetic energy. The Orion bar is not that hot overall, so its presence in such excess is a glaring clue. It points to something violent happening on microscopic scales within the cloud's fabric. The leading explanation is that CH+ is a direct tracer of energy dissipation. Think of the interstellar medium in such a region not as a calm gas, but as a churning, supersonic fluid. This turbulence is like a vast, chaotic ocean with waves and eddies of all sizes. When these waves of energy, finally break like a wave crashing on a shore, their energy is dissipated as heat in tiny, localized pockets. It is in these fleeting, scorching hotspots within an otherwise cool cloud that the conditions become perfect for forging CH+. The carbon and hydrogen, instead of gently meeting, are slammed together with such force that they bond, creating the ion before the surrounding cold quenches the reaction. So, the overabundance of this ion is a chemical signature of turbulence dying. It is a fossil of a shock wave, a marker of where the galaxy's raw, chaotic motion is being converted into heat and chemistry. This process is something we understand in theory but struggle to quantify in the complex reality of space. How exactly does this turbulent energy cascade down to the smallest scales? How efficient is it at creating these localized furnaces? The CH+ mystery is therefore a probe into the hidden thermodynamics of the interstellar medium. It reveals that between the grand scales of stellar radiation and the slow creep of gravity, there is a middle realm of pure, dissipating motion, a realm that leaves its signature in a single, unexpected ion. By decoding this signature, we are not just solving a chemical puzzle. We are learning to read how the galaxy's violent motions ultimately quiet down, seeding the clouds with the unique chemistry that will one day become part of new worlds. The chemistry of a single ion reveals a hidden turbulence, but that same chaotic energy shapes the most common substance in the cosmos. Drifting through the galactic disk are vast, silent reservoirs of atomic hydrogen, the raw fuel of future stars. We map these HI regions by the faint 21-centimeter radio whisper emitted when the spin of a hydrogen atom's proton and electron flip. This simple signal has painted a detailed portrait of the Milky Way's spiral arms, but it has also revealed a profound puzzle. The temperature and density of this ubiquitous gas do not follow a simple, smooth gradient. Instead, they exist in two starkly different states, locked in a perpetual, churning dance. This is the two-phase model of the interstellar medium, and its very existence defies a quiet universe. In one state, we find the cold, neutral medium. Picture a fog bank in deep space, with temperatures hovering around 100 degrees above absolute zero and densities of tens to hundreds of atoms per cubic centimeter. These clouds are the potential stellar nurseries where atoms can eventually pair up into molecules and begin the long collapse toward star formation. They are dark, quiet, and fragile, yet sharing the same galactic volume is its opposite, the warm neutral medium. This is a diffuse, tenuous haze with temperatures soaring to several thousand degrees and densities of less than 1 atom per cubic centimeter. It fills the spaces between the cold clouds like a scorching, invisible atmosphere. The mystery is not that these two phases exist, but how they can coexist side by side without one immediately destroying the other. Why doesn't the searing heat of the warm medium instantly evaporate the delicate cold clouds? The answer lies in a dynamic balance, a constant cosmic simmer maintained by violence. The galaxy is not a peaceful place. It is a battlefield of energy injection. Supernovae are the primary artillery, their shockwaves ripping through space, compressing some gas into cold filaments while simultaneously heating vast volumes to blistering temperatures. Massive stellar winds from young, hot stars add to the fury, carving out bubbles and adding more heat. even the gentle pressure of starlight itself plays a role. This relentless bombardment creates a self-regulating cycle. Imagine a pot of water on a stove set to a constant medium heat. The water does not reach a uniform temperature, instead it convects. Bubbles of hot water rise from the bottom while cooler water sinks to be reheated. The interstellar medium operates on a similar galactic scale principle. The cold clouds are not permanent, static objects. They are temporary condensations like droplets in a turbulent steam cloud. A supernova shockwave might compress a region of warm gas, cooling it rapidly and seeding a new cold cloud. Meanwhile, a nearby blast of ultraviolet radiation from a hot star or the edge of a supernova remnant can strip atoms from a cold cloud surface, heating and evaporating it back into the warm phase. The cold clouds are both products of and prey to the violence around them. This constant churning is what allows the two phases to persist in a rough equilibrium. The cold clouds provide the dense material for star formation, while the warm medium acts as a dynamic pressure blanket, confining the clouds and mediating the energy from stellar explosions. Without this hot, diffuse component, the cold clouds might simply dissipate. Without the cold clouds, there would be no fuel for new stars to continue powering the cycle. They are two sides of the same coin, locked in a feedback loop where creation and destruction are inseparable partners. The precise details of this interaction, how quickly clouds form, how long they survive, how efficiently they exchange material, are still active frontiers of research. Supercomputer simulations try to replicate this cosmic weather, showing a frothy, ever-changing landscape where phases mix and separate over millions of years. The neutral hydrogen map of our galaxy, then, is not a static snapshot. It is a single frame from a billion-year film, a momentary arrangement in a ceaseless, energetic dance between the cold, dense seeds of tomorrow and the hot, thin breath of yesterday's explosions. This dynamic duality is the fundamental state of the galactic ecosystem, the reason the interstellar medium is never still, always poised between a calm reservoir and a storm of potential. Within a few hundred light-years of the galactic core, the rules of space itself seem to break down. This is the central molecular zone, a place of terrifying extremes. Here, the interstellar medium is not a thin haze but a crushing, churning maelstrom. The density of molecular gas is thousands of times greater than in our quiet neighborhood, packing enough raw material to forge tens of millions of stars. Yet, this presents a glaring paradox. At the very doorstep of a supermassive black hole, in an environment ripped by fierce radiation and gravitational tides, we find the single largest reservoir of star-forming fuel in the entire Milky Way. How can such a dense, cold cloud survive in what should be the most hostile kitchen in the galaxy? The first layer of the mystery is its sheer existence. Logic suggests that the violent history of this region, the fermi-bubbles, the Mercati geysers, the constant gravitational tug of war with Sagittarius, a star, should have blown this gas away long ago, or at least heated it to a state where molecules cannot form. The fact that it remains, and in such staggering abundance, means something is constantly feeding it, or it is being protected in a way we do not yet understand. One compelling theory points to the galaxy's large-scale structure. The central molecular zone sits at the bottom of the Milky Way's gravitational well. Over billions of years, gas from the inner spiral arms may have been funneled inward, flowing down this cosmic slope and accumulating in a vast, swirling disk around the core. It is a galactic traffic jam on an epic scale, where incoming streams of gas pile up, unable to proceed further without being disrupted by the black hole's fierce influence. But this leads to the second, even stranger part of the puzzle. Why isn't it all turning into stars? With so much cold, dense gas crammed into such a small volume, we should see a spectacular starburst, a firestorm of creation outshining all other regions of the galaxy. Yet, the star formation rate here is strangely suppressed. It is active, yes, producing brilliant clusters like the Arches and the quintuplet, but it is far less than what all that raw material should allow. Something is holding back the collapse. The answer appears to be a combination of sheer turbulence and magnetic mayhem. The gas in the central molecular zone is not calm. It is supersonically turbulent, moving in chaotic, violent motion stirred by the gravitational pull of the black hole, by supernova explosions from the few massive stars that do form, and by the sheer crowded pressure of the environment itself. This turbulence acts like a constant, violent shaking, preventing the gas from settling into the stable, dense cores needed for widespread gravitational collapse. It is like trying to build a house in the middle of a perpetual hurricane. Furthermore, the magnetic fields here are thought to be immensely strong, threaded through the chaos like a network of steel cables. These fields provide additional support, propping up the gas against its own weight. The process of ambipolar diffusion, where neutral gas slowly slips past these magnetic lines, happens here, but it is fighting against a maelstrom of disruptive energy. The black hole itself plays a dual role. While its tidal forces can tear clouds apart, preventing their collapse, its gravitational pull might also be responsible for compressing gas streams as they whip around the core, occasionally triggering pockets of star formation in a sporadic, chaotic fashion. The zone is a battlefield where the black hole's gravity and past outbursts both stir the pot and occasionally light a fire, while the resulting turbulence and magnetic fields work to keep the lid on. We are left with a portrait of dynamic frustration, a colossal fuel tank sitting next to a cosmic engine, but the fuel lines are kinked, tangled, and constantly shaken. This zone may represent a temporary, unstable equilibrium, a buildup of material that will eventually, in fits and starts, feed both the monster at the center and the brilliant clusters around it. Studying this chaotic nursery is like watching the control room of the entire galaxy, where the forces that govern star formation and black hole growth are locked in a tense, invisible struggle, deciding the future of the Milky Way's very heart. These interstellar wanderers force us to look beyond our own solar backyard. In 2017, a strange, fast-moving object was detected hurtling past the Sun. It was named Oumuamua, Hawaiian for scout or messenger. This was no ordinary comet or asteroid from our own system. Its extreme speed and trajectory proved it was a visitor from another star, the first interstellar object ever confirmed. Then, in 2019, a second traveler, Comet Borisov, entered our view, this one displaying a classic, fuzzy coma of gas and dust. These two mysterious guests are our 28th enigma, raising profound questions about the building blocks of planetary systems across the galaxy. While they are not part of the interstellar medium itself, their epic journeys are made through it, and their origins are deeply tied to the chaotic nurseries around other stars. The central puzzle is their birthplace. Where in the vast galactic disk did they come from? The leading theory is dramatic ejection. In the early, violent days of a young planetary system, gravitational interactions between giant planets can act like a cosmic slingshot, flinging smaller bodies, asteroids, comets, and planetary fragments out into the void at speeds high enough to escape their star's gravity forever. Oumuamua and Borisov are likely such castaways, doomed to wander the darkness between stars for millions or even billions of years. But from what kind of system were they expelled? Their physical properties offer tantalizing, if frustrating, clues. Oumuamua was particularly bizarre. It showed no visible coma or tail of gas, suggesting it was rocky or metallic, more asteroid than comet. Yet, as it departed, precise measurements revealed it was experiencing a tiny, unexplained acceleration that could not be attributed to gravity alone. The most plausible explanation was outgassing hidden jets of gas acting like a weak rocket, implying it was, in fact, a very old, dehydrated comet whose surface had been baked by cosmic radiation into a hard, insulating crust. Its shape, inferred from wild brightness variations, suggested an extremely elongated form, perhaps like a cosmic pancake or a cigar, unlike any natural object we see in our solar system. Comet Borisov, by contrast, was more familiar, a classic icy comet venting gases like cyanogen and carbon monoxide, a composition that looked surprisingly similar to comets from our own Oort cloud. This similarity is itself a clue. It suggests that the basic ingredients for planetary construction, ices, rocks, and organic compounds, may be universal, forged in the protoplanetary disks around countless stars. Yet the differences are just as telling. The strange shape and behavior of Oumuamua hint at formation processes or evolutionary histories we have not witnessed here. Did it form in a system with wildly different gravitational dynamics, perhaps around a binary star? Was it a fragment of a shattered planet or a shard of crust from an exotic, icy world? Each possibility is a window into an alien solar system's architecture and history. Their solitary journeys also map the unseen flow of the galaxy. By tracing their paths backwards, astronomers attempt to pinpoint their home stars. This is a formidable challenge, as their millions of years voyage through the turbulent interstellar medium and past countless stars makes a precise origin point nearly impossible to find. They are like bottles washed up on a beach carrying a message, but the ocean currents have erased the return address. Their very existence, however, tells us something staggering about the galaxy's economy. The fact that we detected 2 such visitors in just 2 years implies they are incredibly common. Estimates suggest there could be trillions of similar objects drifting through the Milky Way, a vast, invisible population of cosmic driftwood filling the spaces between stars. This unseen archipelago of frozen and rocky worlds represents a previously unrecognized component of the galaxy's mass and a potential delivery system for probiotic materials. Could these nomads have seeded young planets like Earth with water and organic molecules, not just from our local sun, but from stars hundreds of light years away? Every Oumuamua and Borisov that passes through is a fleeting sample, a tiny piece of another world's story, hurled into the dark by gravitational chaos and now whispering secrets about the diversity and interconnectedness of all the solar systems we have yet to see. Woven through the cooler phases of the interstellar medium is a ghost of unimaginable heat. In certain regions of our galaxy, space itself is filled with a searing plasma that glows at a temperature of over 1 million degrees. This is the coronal gas, named for its similarity to the Sun's own scorching outer atmosphere, the corona. We cannot see it with our eyes. It reveals itself only as a faint, diffuse glow in the X-ray part of the spectrum, a whisper of the most energetic light. Its existence is a direct consequence of galactic violence, likely heated by the relentless shockwaves from supernova explosions that ripple through the galactic disk like tsunamis of pure energy. The presence of this gas is not the mystery, its behavior is. How does this blistering plasma, with enough thermal energy to vaporize planets, manage to exist alongside the frigid clouds of the cold neutral medium without instantly vaporizing them? The puzzle lies in its distribution, its cooling, and its paradoxical mixing with the cooler phases. We might picture the interstellar medium as a cosmic soup with ingredients at wildly different temperatures. The coronal gas is the boiling broth, while the cold molecular clouds are the ice cubes dropped into it. Common sense says the ice should melt instantly, and the broth should cool rapidly, leading to a uniform, lukewarm temperature. Yet the galaxy maintains both extremes side by side for millions of years. This means the mixing is not simple or efficient. The hot gas likely exists in a frothy, tenuous structure, forming vast bubbles and tunnels, like those in the local bubble, whose walls are the cooler, denser material. The interface between a million-degree bubble and a cold cloud is a frontier of incredible complexity. When the hot plasma contacts the cold gas, it doesn't just flood in. It creates a thin, turbulent boundary layer where heat is conducted and radiation is emitted. This process can actually wrap the cold cloud in a protective sheath of slightly cooler, but still very hot gas, somewhat insulating the dense core from the full brunt of the heat. The cooling of the coronal gas itself is a slow, leaky process. It does not cool by simple contact, but primarily by radiating away its energy as X-rays. However, this plasma is so incredibly diffuse, perhaps only 1 atom per cubic meter, that atoms rarely collide to emit that radiation. This makes the cooling timescale surprisingly long, on the order of millions of years. It has time to flow and shape large-scale structures before it loses its ferocious heat. The greatest mystery is how this hot gas eventually joins the cycle to form new stars. It must cool and condense to become part of a cold molecular cloud, but the path from 1,000,000 degrees to 100 degrees is not a straight line. One compelling theory involves the mixing of phases through turbulent entanglement. As a supernova shockwave plows through space, it can shred cold clouds and inject filaments of cool material directly into the hot bubble. Conversely, fingers of hot gas can penetrate the clouds. In this turbulent mixing zone, the hot and cold gases don't instantly equilibrate. Instead, they create a mist of intermediate temperature gas that can radiate its energy away much more efficiently than the pure coronal plasma. This process, called turbulent mixing layers, might be the galaxy's primary radiator, the place where the immense energy of stellar explosions is finally converted into light and lost, allowing the hot gas to cool and eventually rejoin the reservoir of star-forming material. Understanding this is like deciphering the galaxy's central heating and cooling system. It dictates how energy from dying stars is recycled, how the different phases of the interstellar medium communicate, and ultimately how the raw fuel for new stars is prepared. The faint X-ray glow of the coronal gas is therefore more than just a sign of past violence. It is the active signature of the galaxy's thermal heartbeat, a pulse of heat that must somehow find its way back to the cold and the dark to begin the cycle of creation all over again. This brings us to the final and most speculative frontier of all. Could the interstellar medium, this vast cosmic ocean of radiation, dust, and cold, be more than just a chemical factory? Could it be a conduit for life itself? The theory that suggests this is called panspermia, the idea that life, or its complex molecular precursors, can travel between star systems, seeding planets with the spark of biology. It is a staggering thought that a microbe or a strand of complex organic matter might survive an epic journey across the light years, sheltered inside a comet, an asteroid, or even riding on a microscopic grain of dust. But is such a voyage even remotely possible? The interstellar medium presents a gauntlet of lethal challenges. First is the cold, the deep, near absolute zero chill that slows chemistry to a near standstill. Then there is the vacuum, the profound emptiness that would cause any unprotected cell to instantly desiccate. Most formidable of all is the radiation. The space between stars is flooded with cosmic rays, high-energy atomic nuclei that can shred complex organic molecules and fatally damage genetic material. Ultraviolet light from distant stars adds another layer of sterilizing energy. It seems like a perfect recipe for destruction, not preservation. Yet, nature on Earth has shown us a profound resilience that forces us to reconsider. We have discovered extremophiles, bacteria, and other microorganisms thriving in places we once thought utterly inhospitable. There are microbes living in the boiling waters of deep-sea hydrothermal vents, in the crushing pressures of ocean trenches, and most tellingly, locked within rocks and permafrost in Antarctica and Siberia. Some of these organisms, known as tardigrades or water bears, can enter a state of suspended animation called cryptobiosis. In this state, they dehydrate their bodies, shut down their metabolism almost completely, and can withstand the vacuum of space, intense radiation, and temperatures just a degree above absolute zero for years, even decades. If such hardy life exists on Earth, could similar organisms in a dormant state survive an interstellar journey? The vehicle becomes crucial. A large comet or a water-rich asteroid could provide a near-perfect arc. Its icy interior would shield against radiation and vacuum, maintaining a stable, cold environment for millions of years. A rocky meteorite could offer similar protection, with its pores and cracks acting as tiny shelters. Even a dust grain coated in layers of ice and organic goo might serve as a microscopic life raft for complex molecules, if not a full cell. The journey would be long, millions or billions of years, but for a cryptobiotic organism, time itself may not be the enemy. The greatest hurdle might be not the journey, but the bookends, the violent launch and the fiery arrival. To escape one solar system, a rock would need to be ejected by a massive impact or gravitational slingshot, an event that generates tremendous heat and shock waves. Then, to seed another world, it must survive atmospheric entry and impact without being incinerated. We know some meteorites do survive, landing on Earth with their internal structures and even amino acids intact. Experiments on the International Space Station have shown that certain lichens and bacterial spores can survive for years on the exterior of the station, exposed directly to the space environment. This does not prove panspermia happened, but it demonstrates that the individual steps of the process are not impossible. The profound implication is this: if life can hitchhike between stars, then biology may not be a rare, isolated phenomenon that springs up independently on each habitable world. Instead, it could be a galactic infection, a single genesis event whose offspring spread slowly from system to system, carried by the natural commerce of comets and debris. Our entire planet and every living thing on it could theoretically be descended from ancestors that arrived on a rock from another star. This final mystery reframes our entire search for life in the cosmos. We are not just looking for other islands of biology. We might be looking for our own cosmic relatives, scattered across the dark by the silent, patient currents of the interstellar medium. It suggests that the emptiness between the stars is not a barrier but a potential highway, and that the seeds of existence may be far more durable and far more traveled than we ever dared to dream. This silent highway of potential life brings us to the end of our journey through 30 cosmic enigmas. We have crossed a landscape of ghostly atoms and searing plasma, navigated colossal bubbles blown from the galactic core, and witnessed the delicate chemistry of life's ingredients forming on specks of dust in the dark. Each mystery, from the missing baryons to the panspermia possibility, reveals a single, transformative truth: the so-called void between stars is not empty. It is a dynamic, chaotic, and breathtakingly complex frontier, the very fabric from which everything we know is woven and rewoven. This interstellar medium is the galaxy's circulatory system, its chemical refinery, and its memory, holding within its tenuous grasp the complete story of cosmic evolution. To solve its puzzles is to unlock the fundamental processes that ignite stars, shape galaxies, and possibly seed the emergence of life across the cosmos. The next time you look up at a dark, starry sky, remember you are not looking at a blank canvas, but at a living, breathing entity filled with more questions than answers. We have only just begun to listen to its whispers. Which of these 30 mysteries captured your imagination the most? Let us know in the comments below. And if you enjoyed this deep dive into the unknown, be sure to subscribe. Our journey through the universe's greatest enigmas is far from over.